Okay, in this podcast, we're going to talk about how you know when you're reaching equilibrium, or what I like to call, are we there yet, right? You all remember being in the back seat of the car, going on a trip with your family, and asking your mom or dad, are we there yet? Are we there yet? Okay, so let's take a look. So when you are, imagine you have a reaction, and normally what you start with is a reactant. So reactants, here we have N2O4 becoming 2NO2, right? So imagine in the beginning of the reaction you have just reactants, right? And as they get used up, their concentration declines. Likewise, you start with no product, and as product gets formed, eventually the formation of that product starts to slow down. Okay, so if you're looking at a time concentration graph, you will identify that you are at equilibrium when those two lines go flat. So here we have concentration of NO2 and the concentration of N2O4 are both flat, meaning you're at equilibrium. You will notice that the concentration of NO2 is twice the concentration of N2O4, which is consistent with the balanced equation. Okay. Now, it depends on, each reaction is different depending on the balanced equation. You could have graphs that look like this and like this, where the lines never cross. All you're looking for is what is the point at which both lines go flat. That tells you you're at equilibrium. You can also look at particle diagrams and identify when you're reaching equilibrium. So here we have a storyboard starting at 0 minutes and going up to 48 minutes. And we can follow, here we have H2, right, plus Cl2 giving us 2 HCl. And in order to determine when you're at equilibrium, you can follow any one of these three and look at what's happening to the concentration of them. So from a particle standpoint, let's go ahead and let's count which one we think is going to be easiest. So I'm going to count H2, but it doesn't really matter. I could also count Cl2 or HCl. So here I have, in the initial, I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and I'm counting 8 H2s, right? Here I have 1, 2, 3, 4, 5, 6, 7. Here I have 1, 2, 3, 4, 5. Here I have 1, 2, 3, 4. 1, 2, 3, 4. And I could call these particles or moles or anything. But here is when I know I've reached equilibrium, because the concentration, or the number of particles of the reactant, in this case H2, has become constant. Now let's just do it with using HCl and show you that it's going to be the same thing. So here I have no HCl because it hasn't formed yet. I only have product. I only have reactant. Here I have, let's see, looks like 4 HCl. Here I have 1, 2, 3, 4, 5. I'm a little bit blind. I need to get my glasses so I can see this. So here I have 1, 2, 3, 4, 5, 6, 7, 8 HCl. Here I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 3, 4, 5, 6, 7, 8, 9, 10, looks like about 11. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. You know, I still have 11. Okay. So I can look at any of these. I can look at H2, Cl2, or HCl, and when any of them go constant, the others will go constant at the same time. Okay. I can also look at this data as a graph, of course, and here I have it looks like my counts weren't quite right, but here I have my counts of HCl, H2, and Cl2 along the way. So at what point is this system in equilibrium? 0, 12, 24, 36, or 48 minutes? Well, hopefully you answered that at 36 minutes I've reached equilibrium, because I can see that the concentration of H2 in Cl2 and HCl all become constant. Alright, so here, try this one. A reaction A plus B yields 2C, progresses from, let me see, from A, B, C to D. At what point does the system reach equilibrium? Okay, so again we can follow either reactant or product, and here we have, I'm going to follow C. It looks a little easier than the others, and here I have 2, 4, and 4. So at step C, I have reached equilibrium, and it's gone flat. Okay. Now the last chart we looked at was the time versus versus concentration. Remember, and we had concentrations that did not hit each other. Well, here when we plot time versus rate for a reaction, when we reach equilibrium, what we do see is that these lines will hit each other, because what we're looking for at equilibrium is that the rate of the forward equals the rate of the reverse. And that's what you end up seeing right here. So the reaction hasn't stopped, it has just reached the point where the concentrations won't change, but the rate of the concentration change versus time is now constant. Okay, so you can show this either in a time rate or a time concentration graph, see where equilibrium is occurring. Alright, so which of these equations, following statements is true? A, the forward reaction rate is always faster than the reverse. The forward reaction stops when the system reaches equilibrium. Or C, the system is at equilibrium can have both reactants and products in the reaction vessel. Okay, we're going to stop right there.